All right, so I spent a lot of time thinking about this memory consistency model and how things probably are actually implemented and so on. And I put together some examples so we can sort of explore this a little bit with actual code. So that's what we'll do mostly today. There's a new homework out if you didn't see it. The website is working again, so that's good. The homework is there's a data structure, a tree, that just isn't working quite right. It's running way too slow, and it's having some correctness problems too, and job is to figure out what's wrong with it. Next one will be a parallel, probably a parallel version of the same tree, so we'll see how we can make it run fast on multiple cores. I apologize for the grading. We still haven't returned grades from homework 1 and homework 2. The reason is that our TA has disappeared, and I don't really know what's going on. I'm not in touch with Ben. He's been away for 2 weeks out of contact, and I hope everything's okay with him. Pretty soon I will start grading myself, but we'll see what happens. Okay, so I wanted to get back to this model with the what happens with memory accesses as you access as you run code on multiple cores at the same time. And if I seem a little slower than usual, it's because my own CPU is running at half speed with lots of losses. I have a cold and it's not working well. But anyway, why don't we just start with a simple example first, and then take it from there. So I had a couple of programs. One will explore the performance of some multi-threaded thing, and then we'll start looking at the memory consistency with the ordering. Let's see if we can get the performance stuff first. What did I call it? Two increments, there it is. Okay, this looks good. All right, so this has nothing to do with consistency, but it has something to do with how memory operations are implemented in the CPU, and perhaps we'll recall some of the things we talked about before. So this little program, it basically just starts I don't think we need this measurement. It starts 2 threads running a function each, and then we wait on a barrier. See these 2 threads, they both wait on the barrier, and the purpose of that is just to try to get the threads to run roughly synchronized, roughly at the same time, right? As we found out last time, it doesn't really get you synchronized, right? You'll be in the order of hundreds of microseconds, maybe. Wasn't it like something like that? A little better than that, perhaps. I think it was in the tens of microseconds, usually. But there's no guarantees whatsoever with a barrier. The guarantee is that they won't start running until all 3 have gotten to the barrier. But when they actually will start running after that is a little unknown. Okay, so what are they doing? The main thread, it sleeps for a second and then sets this variable stop to 1. And here's the 2 threads. They're each incrementing a separate variable. So thread 1 is incrementing x, thread 2 is incrementing y, until the stop is set to 1. And these are all volatile, so it doesn't get optimized out. Okay, so maybe we should try to estimate first how quickly this will run. I think that's usually a very good idea. Profilers are great, but they don't always give you the right answer, and when they do, they still don't tell you if it could go faster. They just say, like, this is where we're spending our time. So it's a very good idea to have a rough model in your head of how quickly this should go. So let's see. Looks like we have a read of a variable that doesn't change except for one time. And then we have an x++, so that would be a read and a write. And from this, so x++ would be a move to a register and a plus and a write back from the register. Or if we were to use that inc instruction, it's the same story except now it's in micro-ops instead. So you would have a load micro-op and then the increment micro-op and then a store. It doesn't make a difference in terms of execution speed. You can do the moves, you can do the inc, same thing. Okay, so looks like this one is almost always true, right? So we're going to do well on the branch prediction. That seems fine. But we still have to do this load, I suppose. So that might be 4 cycles there. But it's probably in parallel with this. Here's a load and a store. And so think the CPU, it does 2 loads and a store per cycle. Maybe those are dependent, but we ought to be able to do something like, so it's 2 gigahertz, like maybe we should be in the order of 1 billion, right, per second, something like that. What do you think? Maybe a little less than 1 billion, right? But it's not that it shouldn't be like 10 million, right? It should be in big numbers like that, I would think. So, and the barrier only happens once, so there's no weird synchronization or anything. So why don't we just compile that? With optimization, of course. I think it's kind of interesting, this thing with optimization and no optimization. Like, why does the compiler by default compile without optimization? Because it would seem like the compiler is there to write good assembly for you, so why do we do without optimization? What do you think? Yeah.
To make sure that I guess progressively doing it might make sure that the assembly that we are generating is correct for the needs of the program, I guess. Making sure that we're not doing, I guess, producing a bad assembly like that.
But so I guess my question is, why isn't it by default 03 or 02? It's by default 00. Yeah.
I suppose it might take more time to compile, and second, it has to debug.
Okay, yeah, that takes more time to compile, yes, although I never noticed. But if you are compiling something big like LLVM, that can actually probably take quite a bit of time extra. And then in terms of debugging, what do you mean?
If I want to debug my existing program, if it is optimized out, I probably won't be able to see all the variables.
Gotcha, right. So if you compile with -G to get the debug symbols, then sometimes the line number is just way off. Like you're waiting on you have a break on some instruction, but it doesn't really correspond to a line number, or maybe that instruction moved up ahead of the loop or things like that. So that's a very good point. I think if you compile with -G, certainly you don't want optimized code. Any other ideas? I think one other reason is that while the optimizing compiler always produces correct code, unless it's buggy, which it is, but not that buggy, then it's not clear that the programmer writes correct code. So when you do things like declare a global variable and you increment it, most programmers probably don't think of, oh, maybe this one should be volatile, right? Or you don't think of it at first. So you're more likely to get a program that actually runs if you do it without optimization, because it just doesn't do all those strange transformations of the code that are possible if you assume that the program is correctly written. But if the program is just kind of written as a sketch of, like, yeah, this is sort of what I want done, then without sort of strict declaration of all the variables and so on, then probably without optimization is better as well. I think that's why. I think that a compiler writer wants to be on the user's good side. Like, yeah, this program works. I compile it with GCC, it works. And then when you ask for optimization, then you kind of expect that, oh, yeah, maybe I should have fixed this. Right? Then it's my fault. But if it doesn't work, you just write it with GCC, compile it with GCC, and the program doesn't work, then you kind of get upset and you switch over to the other compiler that doesn't optimize. I think that's what's going on. Okay, anyway, in this case we have volatile, so we would expect the compiler to not compress this loop into something weird. I think if we didn't have volatile on any of these, probably wouldn't do anything. Actually, I don't know what it would do. Maybe it would run forever, probably, because it wasn't stopped in the beginning, so it'll run forever. All right, let's try this out. I think I'm printing out the time at the end. Oh, I am printing out, not the time, because we run for 1 second. I'm printing out how many operations we got in millions of operations. Just the sum of the two, but that's okay. Okay, so there it is. We see that? It's maybe a little small. But it seems way off. I would have expected maybe about 1 billion, ideally per thread, right? But here we're talking about 63 million, 70 million per thread. That's terrible. What's going on? So how long are we spending here? Let's call it 100 million each, right, to make it easy. That means we're spending 2,200 cycles per timer on the loop. Right? Or am I getting this wrong? Let's see, 100 million. No, that's not that bad. It's 100 million. Only 22 cycles. All right. That's much better. I blame the code. Anyway, 22 cycles is still terrible. Because if we ran all these things sequentially, like CPU sequentially, how long should it take? All right. It's a read, that's 4 cycles. And then there's a branch, it's 1 cycle. And then there's another read, 4 cycles, and a inc, 1 cycle, and okay, so maybe that's 12. If we run it sequentially, it couldn't be any worse than 15. And here we're at 22. Okay, actually it's worse than 22, right? Because it's not even 100 here. Yeah. So, any ideas? The reads are taking long, but why? So reads take 4 cycles, right, when they're in L1. And why are they not in L1? Well, it's the reads or the writes, but yeah. It's got to be one of those. Not the inc. Though, if you ask perf, it might well point the finger at inc, right? Because the increment is waiting for the read to complete. And so you can't really trust perf for this kind of granularity. All right. The answer is getting, so I think, well, let's do this. So I'm just going to compile and print out the addresses of x, y, and the stop variable. All right, here we go. I mean, they're long addresses, but they look pretty similar. Right? All of that is the same, and then there's just. So that's maybe what you would expect. Can anyone spot the problem?
variables.
Are aligned with the same memory address?
Can you speak up?
Variables are aligned with the same memory address.
They are aligned with the same memory address.
Yeah, but they will end up in the same cache line.
Yes, right. So our, I think these are in, actually, I don't, which order were they? X, Y, stop, okay. So X and Y, can I get ordered, reverse order somehow here? X has a larger number. I guess they like to put the higher addresses higher up in the source file maybe. But yeah, so you have X and Y on the same cache line here. So what's happening is we got like one core trying to write, but it can't write until it's invalidated the cache line in the other core. So now it's waiting for that to happen. And the other core, well, maybe it gets to read from it, maybe not. But in either case, by the time we get to write to it, it's invalidated in the other core. So now it can't access the cache line. Now it has to get the copy back to read it, and then maybe to write to it. If we get lucky, we can do both. But then the first core doesn't have it. So they're all kind of fighting over this one cache line, which is bouncing back and forth between the L1 caches. So there's two problems. One is we are kind of running sequentially here. And the two cores are essentially running sequentially. And the other problem is it takes a long time to move a cache line from one place to the other. We can move very many per second, but the latency is quite high. Depending on which cores they're running on, it can easily be hundreds of cycles. Yeah?
Long is 64 bytes.
It's 8 bytes.
Sorry.
64 bits, yeah. Okay, so we need to fix that. Why don't we do this? What am I doing? Come on, where's my equals? There. Okay, let's try this. Didn't really improve. What happened?
We're not sure where after we put in that.
Yeah.
Yeah.
So this stuff that we put up here, we're just saying there exist variables, but it doesn't actually mean it should have this layout in memory. If you make a struct, it means a little more, right? Then the order is guaranteed, but there could be padding. If you put a character and then an int, the compiler could introduce 7 extra bytes of empty space in between. If you actually want it to be tight, you have to tell it that. And you say that with this little, actually I should, while we're in it, I'll say, if you have a struct, you have to say attribute packed. If you want the struct to not have any compiler introduced padding. Sometimes it won't introduce anything, like if you're compiling without optimization, probably it doesn't care. Right? But sometimes it will. Oh, sorry, we need double parentheses. Right. Okay. So, but that's not the case here. We're just dealing with global variables. All right. So that's no good. Did you notice the addresses didn't actually change? Let's try one more thing. What do you think? Is it going to change or is it going to stay the same? Change it from a 0 to a 1. Okay, so now we're going much faster. Nice. It's actually not that fast, but it's still much faster. So that's good. So we should put ones in our arrays, right? No, that's not it. Okay, what happened? Why did we get... See, the pointers changed here. Now they're well separated.
Maybe global variables are initialized at 0 stored in a different segment of memory.
That's exactly right. Yeah. So if we do a, let's see, read elf minus a to inc, here we should see something. So and this is more of a 361 topic, but basically there's a whole bunch of segments. Let's see, where are they? I think this is it. Oh, that's not it. Oh, here they are. Okay. Right. So the binary consists of a whole bunch of little pieces of the program. Some of it will be the text, right? All the code that we're actually running. I don't know where that is. Here. So it says, okay, from this offset in the file, the code is this long. Somewhere is the length. Not sure. And put it at this address in memory. Right? That's what the loader does. Read all these segments. There's a couple of different segments. There's a read-only data. If you write a string, like a format string, that'll end up in the read-only data segment. If you write a an array that is initialized, like this one, or these variables that are initialized to 1, they're actually allocated in the file itself. So there'll be a 1 sitting somewhere, and that gets mapped in. So here we actually have a 1 and a 1, and here we have a 1 followed by lots of zeros. These are in the binary, and that's sitting in a data segment. And then finally, there's the ones that are not initialized or are initialized to 0. Same thing. Those end up in the BSS segment. And they're 0 by default because the kernel will only give you memory that is cleared anyway. And so it's much more efficient this way for all the zeros. We don't have to actually keep it in the binary. Okay, so that's why when we put a 1 here, it can't go in the BSS segment anymore. Right? And in fact, if we look at the file size, I think we'll also see, okay, so now it's 9 kilobytes, and let me compile this with the, where it's set to 0. It's probably going to be a little smaller. All right, so that's a kilobyte less because we didn't store a 1 and a whole bunch of zeros in the binary. All right, so that's sort of an aside. I think this was still a bad idea. Right? It went faster, so that's nice, but, or at least with a 1 in there, it went faster. But there's no guarantee whatsoever that the compiler is going to put our array in between x and y. That's how we made it faster, but yeah, there's no guarantee. And it's still going kind of slow. Let's try, actually, we only got 200 million, right? So now what? Oh, let me build it again. Did it actually change its mind? No, good. It's nice with a deterministic compiler that does the same thing every time. All right, so the x and the y are well separated. So why are we now still only getting 200 million operations?
You still have to read stop.
Yeah. So both of these threads, they're trying to read the stop, and one of them is actually writing to a variable that's on the same cache line as stop. So again, we have the same problem. Is there a, let's see, so we got 200 million, and this one got 76 million. Okay. All right, so why don't we put another one there? See if that helps. For now. Oh, this is really ugly, right? This is really not something we should be doing, but I think it's a fun experiment. Oh, okay. Is that better? Not really. Yeah.
The array we are allocating, but not using it.
Mm-hmm.
Why doesn't compiler optimize it out?
Ah, why does the compiler not optimize out the array itself? Well, I think it doesn't know that we're not using it. So that would have to be the linker. So these are global symbols. They could be accessed by another object file. So the compiler generates code only for this file. The globals, yeah, they could be accessed by another one that we link with. The linker doesn't do optimization. All it does is tack together .o files and resolve all the relocation entries in all those files, and then it's done. Okay, but it didn't help. In fact, if you look at these variables, they're still sitting next to each other. So that's the compiler being clever. It decided, oh, two of these nice big arrays. Let me put them together. Right? We can't trust it. So if we actually have a desired outcome, we should tell it what we want rather than try to make it happen with some weird side effect. So to tell it what we want, we say attribute aligned 64. And okay, I'll delete this junk. Okay, so now we're saying each one of these variables has to start on an even 64-byte address boundary, right? So they're going to be on their own cache line. So that should be pretty good. I said 64. Well, cache lines are 64, so that should take care of most of it. So let's see what happens. All right. You know, it's still not really what I would hope for, but I think we're doing much better. So we got 400 million, it's not quite a billion, right? But oh well. And these are now nicely separated. You see how it's like even fours in the second, so that's 64, like 40 in hexes, 64 in decimal, so that's what happened. Sometimes, I think in this case it probably isn't important, but there's a prefetcher thing going on, and you may notice this on some occasions that 128-byte alignment is even better, because whenever you access one cache line, the L1 pair prefetcher will also try to fetch the second, fetch another one that's not right next to it in pairs of 128. That's just one of the prefetchers. But because we're so busy reading and storing here, I think that the prefetcher isn't active, but let's see if it makes a difference. No. Maybe it even made it a little worse. No, it's probably the same. There's always noise here. We can't really, to make a conclusion about this, we should really run it many times and take an average and look at the standard deviation. And if the difference between the two means is greater than, say, 2 standard deviations, well, then you can probably say it's important. Otherwise, forget it. Standard deviation here seems to be on the order of 20 million operations or something. Okay. So this effect is called false sharing. It's a really important performance hog in multi-core programs with shared memory in general. There's some tools that try to eliminate false sharing automatically. The compiler sometimes will try to do this too. Valgrind can catch it on occasion. I tried to run this in Valgrind and never finished. What do you know? False sharing is the keyword, and for any variables that are accessed by multiple cores, you want to make sure that you at least are aware of any sharing that happens, like 2 variables that look independent, but they actually are on the same cache line. You want to try to eliminate that. Or at least be aware that they will perform as if they were the same variable. And all this is because the CPU or the caches operate on 64-byte chunks. They don't do variables. Okay, before we move on, any questions on that? Right. Okay, so that brings us to this consistency thing. And I thought I'd try to maybe improve a little bit upon the mental model we had last time on how the machine works. So if you're a theorist, you probably hate the way that Intel describes the x86 memory model. There are no formal description of anything, pretty much. All they do is they say, here's some general principles, and maybe we should look at the principles. These are the principles. And then here are some examples of the sort of the effects of those principles. But there's no good formal guarantees for much. So I guess what I wanted to look at is where this comes from. How did Intel come up with this design, like with these memory ordering principles? And it all comes from like what you can build. All right, you can do it two ways around. You can start from what would be ideal for, say, a programmer or a compiler writer. You could say, okay, we should have this, right? Sequential consistency between all cores, and that would be awesome. But unfortunately, if you do that, you're going to have a very slow machine. Or you could start from the other side. You say, okay, we want this thing to run fast. So there's no consistency whatsoever. And you had that on the old CPUs, the Alpha from Digital. I think Digital doesn't exist anymore, in part because of that. So normal writes were unordered, right, with respect to other CPUs. This means you can run the multi-core machine really fast, because there's no cache coherence traffic at all, basically, except when the programmer explicitly says, okay, now we have to have a fence here. So if you do it that way, now it's going to go really fast. But I think what Intel did was sort of a compromise. They realized, okay, to go really fast makes it really impractical. None of these guys' programs are going to work anymore. So people wrote single-threaded programs for their first decade or 15 years of machines, right? And then suddenly they say, okay, let's try with two, right? Two cores and see what happens. And then all of these programs, they don't work anymore, right? So they have to introduce something that makes it easier, at least, to make your program work. And that's probably how you win the market, right? You have an older machine, and then all this really expensive software that was developed for the older machine, they move it to the new machine, and it works on that one. That's really great. So I think it's sort of backward compatibility that drove it. But of course, serial consistency would be even better. And then the next consideration is performance, of course. So let's just see what's going on. First of all, let's take a quick look at these principles again. So reads are not reordered with other reads. So in a sequential machine, there's only one CPU at this point. You can expect all your reads to happen in the order you write them. I mean, in the order that they are specified in the program. Same thing is true with the writes. Writes can't be speculatively run sooner than it looks like in the program, but they can run later, right? So you keep your reads all together, and of course we have our writes are all together. That's the total store order. Like the writes don't get reordered at all. Same thing for the reads. And now you can't do a write earlier than it looks like. But you can do a read earlier than it looks like. Right? So you can kind of read a stale value. That's the general idea, right? And then we have all this synchronization stuff that we can ignore for now. Okay, so those are the three main things. Writes are all together. Writes are in the order specified. Reads are in the order specified. Writes can't be run earlier than a previous read. Right? You can't sort of proactively finish your write. But reads can be run much earlier if you want. So where's this all coming from? Well, how do we provide a total store order? It's actually pretty easy. Right? You have all your writes, you stick them in the store buffer, and then you just retire one after another out of the store buffer. So you can execute all this stuff sort of out of order, right? As long as all the writes exit the store buffer and become visible to anyone in order. So that's fine. That seems like a cheap thing to implement, right? So that's how Intel made it. So total store order is awesome because now you don't have to have synchronization between every little thing you're trying to do, right? So your program actually mostly will work out of the box. A sequential program mostly will work out of the box on two cores. Okay. Same thing with reads. Like this ordering of reads, that's pretty easy. They do actually the exact same thing. There's a load buffer. So you have this queue of loads, stick all those loads in there, and you only make the results available from a load in order. So the loads may come in out of order, but your program will only act upon the loads in order. Very nice. And very cheap, right? You run everything in parallel, and you just enforce the order at the very end with this little FIFO queue. Okay. And then we have this weird thing where reads can run early. Why would they introduce something like that? Right. So you have your program with a bunch of reads and a bunch of writes in some order. Why don't we just do a total order on them? Well, I guess we want to be able to run something in parallel, okay. But there's another more important factor here, I think, and that's the whole cache hierarchy bit. So if you're reading a value, generally speaking, you're reading it out of your cache. But there's no guarantee about whatever's in the cache. That can be old, right? We don't know what the other processors are doing. They already did a write, but it's sitting in a store buffer somewhere, or whatever their request to get the cache line, that's being delayed, and our value is old. You can't really do anything about that unless you're going to have a totally synchronous machine. So here they're basically kind of giving up on it. They're saying, okay, reads can be stale, like live with it. And that makes things fast. So we have two guarantees. Those are the reads are not reordered and the writes are not reordered. Those are really easy to implement like that. But it's really hard to make sure that a read is of a current value. That's essentially a sequential ordering guarantee. So they don't do that, because that was too hard. And then there's the write thing. So writes cannot be written before, a write cannot move up ahead of a read. You can't sort of proactively finish a write before the reads that were written before it have finished. So this is not data dependencies, right? So we have all these data dependencies where we say, oh, read X, and if X was greater than that, then write to, that's not it. The data dependencies are always there. Those are always satisfied. This is a question of just instructions that look independent. What are the actual sort of implied dependencies between them? How's we're going with that? Right, okay, so how do we implement this thing? If we're Intel engineers, right? So now you have a write, and it's sitting in the store buffer, and we just want it to wait until all the previous reads are done. Pretty easy. Basically, you just kind of timestamp it or something. So you say, oh, you're the 111th instruction, right? Make sure that every instruction, every read before 111th read or write instruction. So make sure just that we've executed everything before we release this from the store buffer. That's it. Simple little check. So that's cheap. So again, Intel will do these things to provide a nice guarantee if it doesn't cost us too much in terms of like coordination between different cores and so on. So this one's really easy. Okay, so that's in a single core. And I think this one is important. The M fence, L and S fence, they're actually not doing much on normal memory. But the M fence says, oh, okay, actually loads can't move ahead of a previous write either. So you can't proactively load. You can't speculatively load anything if there's an M fence between. So we say write, M fence, load. The load is stuck. It can't go up above. But if you don't have the M fence, the load can go way above. Like at the beginning of the function, you can start reading some value if you're unlucky. Yeah?
Can there ever arise a situation where the value in the load buffer is depending on something in the read buffer and it's like kind of a cycle dependence?
Let's see, read buffer, I don't know. You meant store buffer, I
Yeah.
suppose. Yeah, okay. So there's one more little thing that isn't actually probably written in here somewhere to the same. Yeah, but not with all the writes to the same location, right? So that's the part where we said it's called read after write or store buffer forwarding or something like that. But basically, on the same chip, you can reorder any reads as soon as you want or before any writes. But if it's a write to the same value, then you can't. And that makes sense. Like you can't say, oh, x equals 5 and then read x and it's not 5 on a single machine. That would be ridiculous. And so this is what this little thing refers to. And in practice, it's implemented by the store buffer actually capturing any read to see, oh, I have that one, right? If the store buffer has any of the values you're trying to read, you'll get it out of there instead of out of memory. And I think that was the same speed as an L1 access, but I could be wrong. But it's on the same order at least. Usually one wouldn't do that anyway. It would be kind of silly to write to memory and read it right back, wouldn't it? Yeah.
So you mentioned these store buffers last two lectures. Where would it actually be on the die? Where is this like, or in the pipeline, I guess, right? Is it somewhere physical, like in the pipeline, or is it near the L1? I guess I'm not like clear on where. This
I have no idea where it goes on the die, but it's going to be very close to your the execution unit that does stores, I would imagine. Stores and loads, right? They'll be sitting together there somewhere. But yeah.
Sorry, it feels really abstract, like talking about it, and I don't know, everything at this point we've kind of seen it one way or another. So
yeah. I don't think I can zoom in and reliably point you at the store buffer out of those billions of gates. Okay. So that's on a single core. And then on a multi-core, there's a couple of things going on. First of all, you have no ordering with respect to other processors. So you don't know if your write is going to happen before or after some other processor's write. But other writes by the same other processor appear in the same order. Okay, so let's think about Intel's motivations here again, right? So you don't want to directly coordinate like every write between different CPUs. Well, if you want sequential memory consistency, then you have to. Then we have to actually make sure that all the instructions appear in some order that is directly, there's only one order. But if we make a partial ordering instructions, everything will go much faster because there's not that tight integration between the cores, and so that's what we do. So basically, one core will run a little faster than another for a while, and that's fine. It happened to have something in the cache or whatnot. But we guarantee that all writes by the same processor appear in the same order on all other processors. It's actually pretty easy. Right? So now we just make sure that we put our writes in the sort of communication queues going out to the other processors in the same order. And the processors will apply all of our writes in the same order as they arrived. And that's that. So cheap and easy, let's do that. But the interleaving is different, right? So now if one processor writes to ABC, and another processor writes to CDE, right? It's not clear that which writes will, how they will interleave. That's not, there's no guarantee on that. In fact, one processor could observe, I believe, one processor can observe writes in one order and another will observe it in another order, as long as they're just normal writes. But the outcome will be the same in the end. Like the final value in memory after you let things settle will be the same. Okay, I think we will, okay, and then this locked instructions have a total order. Sometimes you really need total order. And so they have these really expensive locked instructions that you don't use much, but they provide what you would expect out of a sequential memory consistency. Sequential memory consistency, again, meaning all these instructions that the cores ran, we can come up with an order, a perfect order of all those instructions, interleave them some way, but there is a way, such that a single core would run it the same, produce the same result. And that's definitely not the case for an Intel multi-core machine. Okay, so let's try some examples. I made a little harness. So called ordering. Doesn't actually do anything at the, oh, actually, let's do it like this. Okay, so this thing, it runs 100,000 trials. We have 2 threads. The threads kind of wait first. Is that a little out of focus? Yeah, sorry about that. I have no idea how to fix that. Make it a little bigger. So each one of these loops is one experiment. So there's 2 barriers. We wait to start the experiment, and then we wait so that the main thread can analyze the results of the experiment, and then we start over. So here we're basically telling the main thread, okay, we're done with the experiment. And here we're waiting for the main thread to tell us, let's go. Okay, so barriers are really nice for this sort of thing. So here, same thing with the barrier, with the main thread. We're basically telling the other threads to start, and then if we haven't finished yet, then we'll, or if we run all our experiments, we set stop to 1 so that next time they go here, they will stop running. I have to do it inside, because if I set it outside, there's no guarantee that both of them will read stop and get the same value. Right? And then you might have one of the threads entering the barrier and the other one not entering the barrier, and they never finish. And so I had to do it on the inside. Tricky stuff. Anyway, that's what happens when you do this is ad hoc synchronization. Right? The stop variable is not something that you would normally use if you can avoid it. Okay. So basically, we run 2 things at the same time, and then we see what happens. And we do it over and over. So let's try a couple of things. Oh yeah, and I'm printing stuff out. So we have these variables, and they're already aligned. I made this macro that puts everything on its own cache line pair. So now that's all gone. The reason that we want this now is if 2 things are on the same cache line, they're going to be sequentially ordered anyway, more or less. Maybe, well, no guarantees. But that's going to be a really dominant effect in the ordering of all these operations. So now they're on different cache lines, so everything's totally parallel in terms of memory accesses. Okay, so we have x and y. Those are the sort of the global variables. And then we have the x read by A and the y read by A, which we sometimes populate. And then the x read by B and y read by B. If you look at the Intel code, they play with registers. Like they're moving values to registers. And it got a little too difficult to deal with register values from the main thread, and I didn't want to deal with all that. So that makes no difference. We're just writing the whatever we observed into another global variable, and that has the same effect. So let's try this thing. So here we're writing 1 to x and 1 to y. And then I'll say x, this is function b, so I'll say x1b equals x, and let's see, yb equals y. So this is sort of the principle behind all of these experiments, right? This is not a very interesting one, I think. Maybe it's kind of interesting. All right, so the idea is they start out at 0. So the main thread sets everything to 0 before every experiment starts over. So everything's initially 0. We set a couple ones. And at the same time, we're reading this. So the values of x and y are going to be 1 at the end of the experiment. There's no other way. But what are the values of x, b, and yb going to be? Yep.
They could take a couple different values. They could both be 1. They could
Yep.
both be 0.
Yep.
They can be x is 1, y is 0, but never x is 0, y is 1.
Okay. Any other bits? So I think the first one is easy. Both 0. Right? This one just ran before. Right? And then long after we start this one, we have no control over scheduling, so that can happen often. And the same thing. This one run first, and then this one. Okay, I agree with you. They can be 0, 0, they can be 1, 1. And they could be, you're saying it could be 1, 0. So I guess this one finished, and then this just didn't get around to running, and then we run this one, the read before. Okay, that's fine. So we should be able to get 1, 0. Why can't we get 0, 1?
The store order guarantee.
Yeah. So we know we're going to write x to 1 first. Let's see. But we could read this one first. So if we order these, let me see if I can write an ordering on the side. Let's see. Do that. Oh, no, that's not good. Like that. So we could say write x equals 1, y equals 1, xb equals x, and then yb equals y. Okay, so if we ran it in this order, oh, that's too small. If we ran it in this order, we would get 2 1s, right? So let me propose another order. Right? Now we get 0, 1. And then can we get 1, 0? Right, so then we could go like that. That's 1, 0. Okay, let's see if it actually happens. Right? Oh. So the thing to keep in mind with all this is usually the bad things doesn't happen, right? It's only sometimes. But we do run this 100,000 times. So we have a fair shot at it. That's really a lot. Okay. What am I doing? First, I sort everything, right? So that all of the lines that look the same are together. And then unique minus C for count eliminates all the copies, but it keeps a count of how many copies it eliminated. Very useful. So there should be at most 4 different lines. Right. Okay, so most of the time, I guess, so you see we're only modifying these 2 variables. We weren't writing to YA. So most of the time, we just finished reading before the writing. No, the other way around. Most of the time we wrote first, and then we read it. Right? But much of the time, we read first, and then we did the writing. But a couple of the times, we wrote one of the variables, and then we did some reading, and vice versa. Okay, so we get all different interleavings here. Really hairy. So if you're trying to do, if you're trying to access different parts of a shared data structure, like this, without locks, that's what you would expect. Most of the time it's fine, Other times, not so much. Okay, let's try another thing. So this is actually what the Intel manual talks about. It's the other way around. Right. I didn't show you this in detail, but you see it reads Y first and then X. So that's actually slightly different. Because now, the previous one didn't require any reordering. Let's try this now. So it's actually, I reorder these first. So now, here, both of them, let's see. Here we can get Y0 and X1. That's fine, but can we get X0, Y1? That now X is 0. We have to be up there for X to be 0, but the read of Y is guaranteed to be before. So we can't really get that one to be 1. Right? We could try to put these, like we could put the Y up. Now that's 1, but then X is 1 too. So we're missing one of the interleavings. So this is guaranteed by the load order and store order stuff. So if we're really clever with how we write our code and we make sure the compiler doesn't reorder it, and let's cross our fingers for that because it's actually not all that obvious. Okay, happened. So that's good. It's not actually completely guaranteed here that the compiler wouldn't decide to change this. If you want to completely guarantee that we get the right assembly, but you don't care about the processor ordering, like you trust the processor, but you don't really trust the compiler, you have to tell the compiler not to cross this boundary. So here, I mean, but the compiler in this case wouldn't reorder it. Because what's the point? Right? They're both reads from, there's no reason. But what if you did it like this? While blah, right, and then change X, and then we do this, right? Now an optimizing compiler, if Y wasn't volatile, would probably move our Y to up there. Actually, let me change Y instead. So now an optimizing compiler would move the X thing to outside the while loop. And now you do have a reordering. And so the compiler can easily do that sort of thing. In this case, it doesn't, but it's hard to predict, really. So if you are very concerned about it, or if you see that you get weird assembly when you're trying to debug your program, you can go like this. This is called a compiler fence, I think. A couple of things going on. I don't know. Most of you have probably seen this inline assembly. This is kind of a weird inline assembly here, but there's the assembly code. And then our outputs and inputs, I think. And then other constraints. So this one says that memory may be changed in between these, or within this bit of assembly. Right. So we can't actually reorder anything that touches memory across this fence. The volatile says the assembly has to appear in this location. So you can't put code, you can't move any code from here to the other side. So these are clobbers. You can also tell it like, oh, the assembly in here changes register RAX. And so don't use RAX. Like, don't leave anything valuable in RAX. All right, we'll get back to that in a little bit. For now, it seems like we're probably okay, but yeah, in fact, I'll just leave it out just to make it a little more readable. Right, it doesn't generate any assembly. That's totally, well, it's almost free. Right? It prevents some compiler optimization, so in that sense, it's not free, but it doesn't generate any assembly. Okay, let's try something else. So the stores are not reordered. That's nice. That's the best part. Stores are not reordered with earlier loads. All right, so we're saying you can't run the store too soon. All right, we're doing everything out of order, but it can't actually appear as if you did this before it was time. So let's see what that is. So we say xa equals x, and then y is 1. And then we'll say yb equals y, and x is 1. I think that's what it said. Yeah. Okay. Y equals 1. All right, so those are the instructions. So what kind of values can we get here? So we're only modifying xa and yb, so those are the ones we're interested in. X and y are going to be 1 at the end of the execution, no matter what. So I will start. They can both be 0. Right? We could run both of these first. So now x will be 0, and then y will be 1, or yb will be 1. Or we could run this one first. So then yb will be 0, and xa will be 1. All right. The question is, could we get, so now we have the 0, 0, we have the 1, 0, and the 0, 1. But could it be 0, 0? Oh, sorry, could it be 1, 1? Yeah. So in order to get 1, 1, we would have to run, let's see. Okay, so we know that this store, if we want y to be 1, the store to y has to be written first. Okay, so now we need this x to move up somehow. It can't move ahead of this one, right? So it doesn't look very promising. Let's try it. Right. So here we have the xa and y and b1. Yeah, okay. Right. So the 1, 1 is not possible because of that guarantee. So how does that actually work? How would you implement this if you were Intel? So I guess we don't let anything out of the store buffer until all previous reads have finished. So we're gonna get the 0 we're gonna get a correct value for one of these, and then we haven't written anything out yet. So yeah, this ordering seems pretty simple. Like we just kind of block the exit from the store buffer. Okay, that one's fine. What about this other one here? This is a really tricky one, so you should take a careful look at that. So this is the other order, right? So now we're writing first, and then reading. So let's just reorder these. So in this case, we're saying, Intel's saying, well, the reads can be moved up, right? Or equivalently, stores can be moved down. Stores can be kind of sitting in the store buffer for a while before they leave. So they can kind of end up late. Or a read can become early because, well, something was already in the cache. We got a stale value, it was quick, we went with it. So it's rare. But very occasionally, we'll have these two cases where it looks like we really should be getting let's see, 1, 0, or 0, 1. Shouldn't be possible to get 1, 1 or 0, 0. Well, maybe 1, 1 is okay. Like you run this, yeah. So we could get like here. Oh, here's 1, 1. That one's pretty easy. Right. Run this, and then the two reads. That's fine. Actually, that seems like it's pretty rare. Extremely rare. We only got 4 of those out of 100,000. So why might that be? Well, we have to be running a really tight ship here. Like these two instructions have to run together before these run. Right? And then all the memory has to get exchanged in between. So it seems like a pretty hard thing to achieve. Okay, but what about the other direction, right? So 0, 0, how do we get to that? Well, that basically the only explanation is that this read happened before. So let's see. So it goes. So it could be like, well, actually, it has to be like that, doesn't it? Yeah. So the reads are moved up. Okay, this is one of those things that can really trip you up. So how do we avoid this? Because it's not all that uncommon. As you write to a data structure, well, ideally you would have a lock. Right? If you have a lock on this whole shared data structure, the shared data structure consists of X and Y together, right? So ideally you would grab a single lock for X and Y, modify them to your heart's content, and then unlock, and then we're fine. Actually, we are fine because locked instructions, that's a different kind of lock now, but atomic instructions are totally ordered in the Intel CPUs. So, and no loads can go before or after, like they can't travel across one of those atomic instructions. That's sort of what enables us to write synchronization operations in the first place. But what if we don't want to acquire a lock on this? We just want to enforce an ordering, right? We want to say, you can't go read until this write has finished. Yeah, unfortunately, that doesn't produce any assembly. Right? It doesn't produce anything in the binary. It just tells the compiler, don't reorder them, but this is not the compiler doing it. It's the processor doing it. So there's a couple things we can do. We know that atomic instructions prevent reads from crossing, like from being scheduled before the atomic instruction or after. Like they can't move across. So we could do that to like access another variable, but there's an explicit one called the mfence that says no reads or writes may cross this boundary. So basically, with an mfence, you have to finish everything that was written before here, everything in the code before, all the reads and writes in particular, have to finish before you schedule the next one. Okay, so let's try that one. Okay. So we eliminated that weird case. The other two, there's nothing we can do about. They're all fine. Right? We run one first, or the other first, or maybe we run the assignments first and then the reads. Both of those, all of those are perfectly valid executions. But now the reads didn't happen before our own writes. So this one I had to think about quite a bit. This seems expensive. And in fact, an mFence is really expensive. It slows down. Now we don't have any performance measurement here because we're doing a whole bunch of printfs in the middle of everything, and that will screw everything up. But an mFence is expensive. But how is this even implemented? Right, we have this whole cache hierarchy. Right, so when we're reading this variable here, how do we know that we have a fresh value? That's what this means. This is what the mFence means. Like, this has to be a fresh value. It can't be some stale stuff in the cache. And a cache, well, by nature, is stale. Right? It's a copy. Maybe it's an old copy. Maybe it's a new copy. But hard to make any guarantees. The mFence does make a guarantee. So what's going on? So you could imagine that the mFence clears the cache. Right? You just clear the entire 16 megabytes of cache every time you have an mFence. I think there is another. There's a CL flush instruction where you can clear an individual cache line, but that's not good enough here because the processor doesn't know which ones we mean, right? Which cache lines. We have some instructions later on, or maybe we meant those cache lines, maybe not. So one way would be to flush the entire cache. But there are no instructions that do that. For good reason. That seems really, really expensive.
We open for educated guesses right now? Or
Yeah, go for it.
Maybe it stalls and waits to see if that buffer that we were talking about has a new value or something like that.
Which buffer are we talking about?
The rewrite buffer that we talked about?
The store buffer, you mean?
Yeah, sorry.
Right, so this is with respect to another CPU's write.
Oh.
So we're doing a read, and we want to make sure that, if anyone else was writing, make sure I get that. But we don't know that they started writing yet. Because that could be happening right now at the same time. And that's when we get all these weird effects, when everything's really closely interleaved. So I think what's happening is they know how long it's going to take for a write to propagate, or there is a cache line invalidation message to propagate from another CPU. So they can guarantee ordering. Well, they know first with the write. This makes sure that our write makes it out to everyone else. That's the main thing. So in order for us to write to a cache line, we have to first, it ends up in the store buffer, right? Before it leaves the store buffer, we have to invalidate everyone else's cache line if they have copies of it. So we send an invalidation message, and we wait for it to come back saying, yeah, okay. And then we get to flush, not flush, but we get to retire that instruction. So now we know that everyone else cannot have an old value of our x1 anymore. Right? Of our x. So it's not so much that we guarantee this one isn't stale. We guarantee that that everyone else has our new value. And then I think we have to wait. We're out of time. But I think we have to wait to make sure that no sort of in progress write on the bus is happening while this mfence is executing. It's probably like a oh, and wait for this many cycles sort of thing going on too. I'm not quite sure. Anyway, we're out of time. The overall idea here, the mfence doesn't let you move instructions across it. That's really important. And I think not for the compiler. The CPU doesn't do it. The compiler doesn't know what's going on here. Only the CPU. The compiler doesn't know what's going on inside of this. But we told it here with this memory. We're saying, like, you can't reorder code across that. Compiler doesn't care what assembly is inside of it. All right. Thank you. I'll see you on Thursday.